Okay, is chemistry kinetic molecular theory of gases over there? According to kinetic molecular theory, gases have these postulates over there, and these postulates is related to that all the particles called molecules are in continuous motion. Motion over there means they have uh, random motion. For example, I am saying that there is a closed container which is having gas particles into it, which are showing their direction in different directions over there. For direction of motion, they are striking with the walls of container over there. They are reflecting back from the walls of the container, and they are showing the random motion over there. They are colliding with each other. They are colliding with the walls of the container over there. So I will say here that their kinetic, because they are in continuous motion, in random motion, their kinetic energy of all molecules is directly proportional to temperature. Temperature means, as we said, that the container is heated up, the kinetic energy of the molecules inside the container will be high over there. After that, number three, uh, the collision of gas molecules is perfectly elastic inside a closed container. Closed container. As in IGCSE, you have studied about that momentum. They are having momentum because they have gas molecules have some mass, they have some velocity, so they have some momentum over there. Their momentum in one direction and in reciprocal direction, both in opposite direction over there, clockwise and anti-clockwise, momentum can be taken into initial momentum and final momentum. If both should be added, will be equal to zero over there. Like if it is having a positive direction in the form of plus 30 kilogram meter per second, on the other end, the opposite direction will have minus 30 kilogram meter per second. So I will say here net value is zero over there. And that is perfectly elastic. At number four, we will say here that the gas molecules will have, will exert pressure on the walls of the container, walls of container over there. So according kinetic molecular theory, kinetic means due to motion, due to the effect of motion which they are having over there, will be considered that they have exerting pressure, they are having temperature relation, they are showing the random motion. Everything is related to kinetic molecular theory. I'm not explaining that gas is having some volume, gas is having some intermolecular forces in the form of van der Waals or like that. That will not be considered over there. After that, at number five, I will say here that we should add here that the actual volume of gas, actual ACT, actual, actual volume of gas in container is negligible as compared to container volume. Means that can be taken as negligible volume. We can say that is not to be taken in the proper consideration over there. If I talk here, according to the main phenomenon that we say how it will be going on and how it should be gone for explanation of kinetic molecular model or kinetic molecular theory, we will have these properties for gas molecules over there. After that, there are some gas laws are given that is related to number one is Boyle's law. Boyle's law. Boyle's law states that pressure exerted on gas volume is inversely proportional to volume, inversely proportional to volume. Pressure exerted on a gas is inversely proportional to volume of gas at constant temperature. For example, here you are having a container which is having a movable lid on its surface. And here you are placing some object over there in the form of complete, I can say a bot of mass over there, which is having some weight in the form of force acting downward. And it is occupying and exerted on some area. So according to the definition of pressure is equal to force over area, I can say it is mg as a weight over area. So force is being exerted over there. And if you double it, if you double the pressure over there of same container, if the gas particles are inside, which are in random motion over there, and the piston at normal pressure of 1 watt is the piston or lid is lying this surface. But when you take this with the 2 watts over there, then what will happen? This volume will be decreased and reached to the downward position over there, which will show that it was its V1. Now it will reach at V2 over there. And I will say here it is continuous and it should be dotted over there. It should be dotted. So here I'm saying that it was the original position. When you have doubled the load over there, then the pressure is being exerted and volume is decreased. Here I will say pressure is inversely proportional to volume according to Boyle's law. And if I say I am taking a constant over there, that this relation it can be properly arranged over there, then I will say here pressure is equal to K over V. And if I am taking here V1 as volume, I will say the pressure will be P1. Then I will say pressure P1 is equal to K over V1. And on the other end, for the second one, I will say P2 is equal to K over V2. Both are having K as a constant over there. Then I can write it P1 V1 is equal to P2 V2 over there. This is called Boyle's law. If we draw the graph between the pressure and volume over there, pressure and volume. When I am increasing the pressure, I'm taking pressure on x-axis and volume on y-axis over there. For example, the pressure is low, I say the volume is here. After that, I am increasing the pressure, volume is decreasing, increasing the pressure, volume is decreasing. Like this, it is happening over there. Like half-life topic in physics over there, the same graph was explained over there in IGCSE. And we can say here, and this curve is called isotherm. And such process in which temperature remains constant is called isothermal process. So Boyle's law is little bit explained now. After that, the second one is Charles's law. Charles's law. Charles's law states that uh, temperature of gas molecules is directly proportional to volume of gas molecules, या volume of gas over there. If I make a proper relation like how it is increasing over there or decreasing over there, then I will say volume is directly proportional to temperature. So volume is directly proportional to temperature. Like I am saying here, V is equal to KT over there. Then I will say here, let's suppose you are having a movable piston over there at this position with the volume V1 and temperature which you are providing with the help of flame, and that you are increasing the temperature over there. What will happen? The volume is V1 and temperature is T1. After some time, what happens? That the container increase its volume as the temperature increased to T2, volume becomes V2. So this relation should be taken as V1 is equal to KT1 and volume 2 will be equal to KT2 over there. If I'm making the relation K as a subject in both cases and equating them, then I will say the relation will become V1 over T1 is equal to V2 over T2. Always remember when I was talking previously pressure will be taken in Pascal and temperature will always be taken for calculation in the scale of Kelvin over there. You will never use for Celsius degree or Fahrenheit degree over there. And if temperature is given in Fahrenheit or degrees, and because in the laboratory, the thermometer which you have will be calibrated in degree centigrade, then for temperature for calculation you want to use, then you will convert degree centigrade temperature plus 273 and your temperature will be converted into Kelvin. Or you have calculated the temperature in the Kelvin and you want to move from your stoichiometry, like from your calculations to practical form over there, then you can say temperature in degree centigrade you want to calculate, then you will use temperature in Kelvin minus 273 degree over there. So you can take this interconversion. We can also use the Fahrenheit, the clinical thermometer, which doctor uses for measuring the fever over there. That temperature in Fahrenheit will be given as 1.8 degrees centigrade, means should be multiplied with 1.8 plus 32 like that. For example, I am saying the human body temperature is 1.8 multiply 37 degrees centigrade plus 32. What the value is, I will get here like Fx. It is 1.8 into 37, 1.8 multiply 37 equals to this should be added with 32 will equal to this, which is equal to 98.6. So we say 98.6 Fahrenheit is our body temperature. Our human body temperature is 98.6 Fahrenheit can be taken over there. After that, after explaining the Charles law, which was we have taken in the form of V1 over T1 is equal to V2 over T2. Now I am going towards Avogadro's laws. Avogadro's law. Avogadro's law states that volume of gas is directly proportional to proportional. One thing more, which I should add in the definition of here, that when I'm saying volume and temperature are directly, pressure is constant over there. And on the other end, when I am explaining here directly proportional to number of moles. And we can take here that volume is directly proportional to number of moles and V is equal to Kn. And here initial number of moles are final number of moles we don't take. We say that it is directly proportional only. And if I go towards the number of moles for Avogadro over there, he said the Na as Avogadro's constant with the substance having the number of molecules of 6.022 multiplied 10 raised to power 23 atoms, ions, molecules can any be in the one number of mole over there. So that is Avogadro's law. If I join all of them together, like I am saying here, volume is directly proportional to temperature, directly proportional to number of moles, and inversely proportional to pressure over there, then I can say here my equation is going to become V is equal to the general gas constant R can be introduced, N R as constant over T with P, and I am getting here PV is equal to nRT. Here, all the variables, which is P is pressure, T is temperature, V is volume, and N is number of moles. And in the last, R is general gas constant over there. In all of these variables, with all of these variables, I will say here PV is equal to nRT, and this N can be taken as number of moles is equal to mass in gram over MR. And if you want to calculate the MR of a gas, then you will just place it here. PV is equal to M mass in gram over MR with RT over there. Then MR you can calculate if you have all other values of the variables. MRT, R is constant over there, which can't be changed for any equation over there, over PV can be taken into account. After that, the general gas constant, which I have taken here, we will have to calculate its value in as general gas constant is having the value 8.316 joule per mole, like that. This is its value per mole per Kelvin also. And if I'm going towards this, then for this one, I will say here, we will have to take SI base units over there. And SI base units. SI base units. SI base units. Pressure 1 atm 101,325 or 1 multiplied 10 is power 5 Pascal. Volume in meter cube. Temperature in Kelvin means 273 added. So 1 atm pressure in Pascal. Volume in meter cube, because 1 molar volume is 22.4 or 24 dm cube at room temperature and pressure. At standard temperature and pressure, we take it 22.4. And temperature is 273 Kelvin, and R is being calculated by putting all of these values over there. So I am using them, that I am going to make R as subject. R is equal to PV over NT. I have used this equation for making it subject for R over there. So pressure, I said 1 multiplied 10 raised to power 5 in the form of Pascal. Volume, I said that at standard temperature and pressure is taken as 24 dm cube. But I am talking to take it in SI base unit, so decimeter should not be used over there. You will have to go for meter cube. then it should be 24 divided by 1000, then it is 0.024 meter cube. 0.024. After that, divided by one number of moles I am taking, and temperature I am taking is 273 Kelvin over there. Just look at here. 273, 0.024, 101,325 can also be taken. So let's take the exact value which should be taken. 101,325. Okay, I'm using these values only for getting my constant. Let's check what he is giving. If he will not be giving exactly like 8.31, then I will use 101,325 as my 1 atm pressure over there. First of all, fraction introduced there. 1 is not having any value over there, so I'm taking 10 raised to power 5 multiply by 0.024 and divided by 273. 73 equals to this, equals to 8.79. 8.79. 8.79. Let's check what he is giving over there value. He is giving the value 8.31. So he has used 101,325, but it should be approximately equal. 8.79 is too much having the difference. I have taken some wrong value over there. 0.0224. Okay. 22.4 it was. It was 22.4. So I should take 0.0224. 0.0224. Now it is giving us this value, and it is 8.205, 8.3, 8.31 is coming now exactly over there. So I can say here that it is having value 0.0224, and it is having 8.3205, 8.205, and then I can say it is 8.2, 8.30, 8.31 is the value which should having the unit joule per Kelvin per mole over there. This is our today class in which I tried to go with the gas laws. I tried to go with the basic kinetic molecular theory of gases over there, and the derivation of general gas constant having the value 8.316 joule per Kelvin per mole over there. Let's check what he is saying over there in the lecture format over there. He has taken, first of all, molecular theory of gases. Gases are consisted of tiny particles which are continuous in random motion. Collision among gas molecules is perfectly elastic. We have discussed this. Momentum is conserved and just velocities are exchanged over there. Pressure of the gas is due to collision of gas molecules on per unit area of the container. The average kinetic energy of gas molecules is directly proportional to temperature. Gas molecules are widely arranged, no forces of attraction. Actual volume is negligible. After that, Boyle's law, where he said inversely proportional, but didn't give some picture to explain that. Just simply P1 V1 is equal to P2 V2. After that, Charles' law, volume is directly proportional to absolute temperature at constant pressure, he has mentioned. V1 over T1, V2 over T2. And he also has mentioned that he can join both of these relations in the form of P1 V1 over T1 is equal to P2 V2 over T2. I should also add it there that just after the volume, here he is saying P1 V1 over T1 is equal to P2 V2 over T2. Should be added. Okay, after that he said Avogadro's law, V is directly proportional to number of moles at constant temperature and pressure over there. After that, Avogadro's law, he has said now by combining these equations, pressure, temperature, and number of moles, he said the general gas constant R is introduced over there, and this R can be taken as a general gas constant. And then he said how to derive this. For PV is equal to nRT. He said mass in gram over molar mass, number of moles formula over there is taken into account. PV is equal to M over MR, and MR can be calculated by using this relation over there. After that, the calculation of SI base units over there, in calculation involving the gas equation, parameters should be taken in the following: pressure in Newton per meter square. 1 ATM is 101,325 Newton per meter square. 1 Newton per meter square, 1 Pascal, like 1 multiplied 10 raised to power 5, can also be taken as a round off value. And then volume in meter cube, and temperature in Kelvin, like 273 Kelvin. At STP, he is saying that the pressure is 1 atm, volume is 22.4 dm cube, so he should take in meter cube over there. After that, he is saying here temperature in 0 degrees centigrade at STP, standard temperature, and pressure over there should be taken into account. And then temperature 273 and number of moles is 1 over there. Beta, are you there?
Yes, can you hear me?
Yeah, I can hear you. All right. Okay. R is in the form of 101,325 and multiply 0.024 divided by 273. So he has got the value joule per Kelvin per mole. I have mentioned it you over there. And after that, he is saying similarly at room temperature and pressure, if you get this value over there, it is 8.31. Again, at room temperature and pressure, like 24 dm cube will be the volume which you have studied in IGCAC for calculating the value over there. Volume is being taken at 24 dm cube. Pressure is same to same over there, but he has taken the temperature of 20 degrees centigrade. And in IGCSE, we were taking 25 degrees centigrade or 298 Kelvin over there. Here he is saying that the room temperature is 20 degrees centigrade, and he is adding and he is getting 293. It's okay, no problem. Number of moles is 1 again. R is equal to PV over NT should be taken. So by inserting the values in the equation, he is getting the general gas constant value as 8.31 as a constant over there. Then he has introduced there an example equation where he is saying 0.275 gram of some compound X when vaporized at 150 degrees centigrade, 720 mmHg. Mercury is millimeter mercury pressure. This is being used for calculation of liquid pressure over there by using barometer. Occupied a volume of 120 cm cube. Calculate in relative molecular mass of X over there. Means you will have to use the same equation, but you will use PV is equal to mass in gram over MR into RT. And you are using this MR to make us a subject over there. MRT over PV should be taken over there, and your molar mass can be calculated. He has taken mass in gram 0.275 gram, staying in gram over there, no need to convert in kilogram like in physics. Temperature 150 degrees centigrade being added with 273, 423 Kelvin temperature. Pressure 720 mmHg. For converting it into ATM, we will have to divide it by 760. That is 1 ATM pressure. So he is saying that you are getting this ATM, and this should be multiplied by 101,325 to convert it into Pascal or Newton per meter square. After that, volume should be taken in dm cube. So he is saying 0.12 dm cube. And by putting all of these values, he has calculated that the MR of the compound of sample X is 84 over there. So this was our general gas equation. If some gas follows this equation exactly, then we will say that is ideal gas. Otherwise, we will say it is showing some deviation and high pressure, low pressure, temperature over there. Some deviations are being shown by the different gases will be discussed in the next class, and we will also move towards kinetic molecular model of the liquids. So ideal behavior of gases. The one thing you should remember, there is no gas which can behave ideally, because temperature of the universe or temperature of the gas is going to increase or decrease over there due to its continuous motion or environmental factors over there. And pressure is also changing, like at sea level it is exactly 1 atm, and the pressure at the Mount Everest or K2 like that is going to decrease. Pressure of atmospheric pressure is going to decrease. So we can say no gas is available in nature to show that it is going to follow the equation of PV is equal to nRT exactly over there. So we can say this is non-ideal behavior, and it can be shown only in cases of different conditions we will discuss in the next class. And kinetic molecular model of liquid, vapor pressure, and then solids, then micromolecules, giant structure. You have discussed this like diamond and graphite, and these structures were explained also early. This will be new one for carbon nanoparticles will be new for you, and nanotubes will also new, and graphene is will be new over there. Then there is metallic lattice. That is easy one, and chapter will be closed. I will try to close this chapter tomorrow, and maybe something will be missing also. All right. Do you have any question related to this topic over there? Beta, are you there?
Yes, can you hear me?
Your sound is too much like faint sound. I have to focus properly. I said, do you have any question now?
No, sir.
Okay, I think so. We are done with almost 15 classes over there, and you don't ask me any question. One thing is clear, you are understanding in a best way, or you are understanding nothing. I don't know.
Yes, I understand.
You are understanding. Okay, my son. Thank you so much for today. See you tomorrow. See you on Friday. All right?
Okay.
Okay, my son. Thank you so much. Bye bye.
Thank you. Yes.